Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Today we are very happy to introduce Dimitris Gerontogiannis, who is our local breed from IMPAN. He recently joined IMPAN, he was in Leiden before. And today he will tell us about the log-LAPLACIAN on, I have no idea how to pronounce this guy, it sounds Scandinavian to me.
AHLFORS.
AHLFORS, regular spaces and the non-commutative boundaries. It's all yours, take it.
Thank you so much, Piotr, and also for the invitation, giving me the chance to speak at this very interesting seminar. So this is work with the first part. I have two parts in this talk. The first part is about work with Bram Messeland from Leiden University. And the second part is work with Bram and Magnus Gothling.
Bram is
great. And Magnus Gothling from Lund University, Sweden. Now, this talk is about creating a framework, differential framework, in spaces that might not have a classical differential structure. Okay? And these are metric measure spaces that have some regularity condition, some nice interplay between the metric and the measure, that they are quite general from the point of view of non-commutative geometry. And I will talk on how to create a framework of harmonic analysis on those spaces, and then how to implement dynamics on those spaces. First things first. This doesn't change.
now, try now.
Yep. Yeah, so this paper, you can find it. First things first, I will present you some background on AHLFORS regular spaces. As I said, these are metric measure spaces. Nope. These are metric measure spaces, and for this talk, we assume the measure is finite. And the regularity condition we require is that the measure, the volume of a ball of radius r around any point, so that's a uniform condition, is of order r to some exponent delta. And by this, I mean you can find uniform constants, C1 and C2, okay? So that the volume is greater than C1 times r to the delta, and smaller than or equal to C2 r to the delta. Now, whenever we have such a measure on a metric space, then automatically delta will be the Hausdorff dimension of the metric space. And in fact, several other fractal dimensions will coincide with the Hausdorff dimension whenever you have such a measure. Moreover, such a measure will be also uniformly bounded above and below by the Hausdorff measure of that dimension. But it doesn't mean that they are the same. Okay? So it really does play a role if you have a nice AHLFORS regular measure, not just the Hausdorff measure. Now, a few examples, and there are many more. You have the compact, we have compact Riemannian manifolds, and you can also allow a boundary.
Sorry, why compact?
Sorry,
why compact?
No, these are examples.
Yes, but with the Riemannian manifold should be compact to
no, not necessarily. They can be open. Yeah, exactly. I'm just putting some, nicer conditions, because I also said like a finite measure, but you can have like open balls.
Riemannian manifold.
Yeah, exactly. And so you take the volume measure and a Riemannian metric, and it's going to be a AHLFORS regular, and the dimension delta is going to be simply the topological dimension, so there is no structure there. Now, you can have several fractals in Euclidean spaces, like Sierpinski gaskets in any topological dimension. Moreover, like starting from an iterated function system that satisfies the open set condition, so-called open set condition, like some regular condition, then the limit set is going to be AHLFORS regular for the Hausdorff measure.
Sorry, do you have examples of fractals which are not AHLFORS regular?
Yes. Yes. I will paint. I mean, there are several examples, but I really like
How Julia says AHLFORS regular?
I think it's not with if you have some regular condition with a harmonic measure, yes. But
it's true that delta should be unique. So if you take disjoint union of two fractals with different delta, then it wouldn't be AHLFORS.
yeah, you're right.
Okay.
So,
But union of two different fractals is not self-similar, so it's hard to say that it's a fractal.
Okay.
yeah, but yeah, good question. Yeah, for instance, here for compact for the Riemannian manifolds, you would like connected or like find many copies of connected, something like that. Example of non-AHLFORS. I hope I can paint it here. So that's an example given by Polycott and Weiss some years ago. And really, you build an iterated function system as follows. You take a nice rectangle, and then you have one map that squeezes this rectangle to the upper left corner. That's too small. Oh. I should make them almost the same. And that's a big eraser. Okay, so you have this, and then you create another map. So I1 and I2. And now, depending on the length of the smaller rectangles, so if they're reciprocals of the golden mean, something really nice, then the resulting limit set will be somehow a under-like structure, and the Hausdorff dimension is going to be strictly smaller than the box counting dimension. So they cannot be AHLFORS regular, because if they were, these dimensions would be the same. I erase. Good. Now, scale spaces are hyperbolic dynamical systems with contractive and expanding directions and local product structures. And you can put somehow like a visual metric, some nice metric, and then the measure that maximizes the topological entropy is AHLFORS regular. Moreover, Gromov boundaries, limit sets of Kleinian groups, several of them are AHLFORS regular, and the measure is the Patterson-Sullivan measure. Okay, so but please interrupt me when you have questions.
What happens
time to...
when R is the diameter? Then what happens when R is equal to the diameter of X?
Nothing. It's just that it's not necessary to put the diameter there, at least for the situations. But this condition that you allow R to be equal to, that you allow...
Finger also works.
Okay. That you allow R to be equal to 0, this really tells you that mu cannot have atoms. And so such a space, the way I've written it down, does not have isolated points also. Okay, but there are generalizations. And in fact, what I will present to you, it extends to more general situations than AHLFORS. But we worked in this because it was general enough for what we wanted to do, and it's also more presentable.
But my question was very stupid, just when R is equal to the diameter, is this condition automatic or is it redundant?
So you just need it locally for this.
So it actually doesn't make sense if X is not a ball.
Yes, exactly.
Yeah.
And also that.
Okay.
That's why I put...
okay, so it doesn't make sense when X is not a ball.
Yes. Yeah. So, changing slides. As I said, we want to extend the notion of Laplace-Beltrami operators on this framework. Now, in the setting of metric measure spaces, there has been considerable work on trying to on extending Laplace-Beltrami operators, like Tigger's work. But AHLFORS spaces don't necessarily need to be length spaces, okay? And they can be quite fractal. And then one needs to work in a different way. But in this talk, we're not only interested in generalizing the notion of Laplace-Beltrami operators, we're interested to generalize it in a way so that it's compatible with dynamical systems in the sense of non-commutative geometry. I will explain more. But going back to the classical situation for a bit, we have the Laplace-Beltrami on a manifold, and now this operator seems quite a lot from the structure of the manifold. Okay, so first of all, it is essentially self-adjoint on the smooth functions. And as you know, essential self-adjointness is a very non-trivial property for an unbounded operator. And moreover, you have information, like topological information from the spectrum of the operator, like the resolvent to some power, it's going to be trace class if and only if T is greater than the topological dimension over 2. And also, it doesn't only see the Laplace-Beltrami, the dimension through its spectrum, but it sees the symmetries of the manifold also. Because if you have an isometry of your manifold, and you view the isometry as a unitary operator on the L2, I should point with this, on the L2 space as a unitary operator, and then you make sense of this commutator in the unbounded way, you need to preserve the domains and so on. Then you have that this commutator is 0 if and only if gamma is an isometry.
And now, please correct me if I'm wrong, but wasn't this property, precisely this property, used by somebody to define quantum isometry groups for spectrum?
Yes, this is what it makes sense. Yes, exactly.
What did I forgot?
Goswami. So that's cool. But we want at the end to build spectral triples. Now, the first thing that one sees if tries to create a spectral triple from the Laplace-Beltrami is that due to the Leibniz rule, you cannot have bounded commutators with functions multiplication operators. In fact, also for non-isometries, typically this is not going to be bounded. So we need to create an operator that sees on AHLFORS spaces that sees a lot of the structure of the AHLFORS of the metric measure space, and at the same time you obtain bounded commutators with non-isometries, because not often you have isometric actions. Okay, and isometric actions are nice, but quite often you have non-isometric actions in spaces. And what I'm trying to say is that having a bounded commutator with non-isometries, or like with some homeomorphism, diffeomorphism, nice map, it means that this map is differentiable with respect to delta. Okay, and this is what we try to create here.
Sorry, may I have a question?
Of course.
I'm a little bit confused about those commutators. So in order to have a spectral triple, you would like to investigate commutators with functions. So commutators with precisely multiplication operators.
Yes.
And here you have commutators with respect to some, okay, you have written lambda, gamma. It should be defined as composition, pre-composition with this gamma. So this is a different flavor. So
no, I mentioned it. Yes, but I did mention multiplication operators, just I haven't written it down, that you don't get bounded commutators.
No. Asking is, what Adam is asking is that your commutator is the commutator of the differential operator and the diffeomorphism.
Yes.
Okay.
Yes.
So, in which sense you have this operator? Yeah, because we are using by gamma some transformation of L.
Yes.
Then
Yeah. So you take the unitary associated to that.
Okay.
Yes. This I understood, but so the second point is not about being a spectral triple.
No, not yet. I'm not there yet. But I also mentioned, without writing it down, that even for multiplication operators with smooth functions, you will not get bounded commutators.
Okay, so these two are different things.
They're
with functions and with the diffeomorphism. Okay.
Yes.
I am.
It's just that at the end, we wanted to construct spectral triples from cross products of non-isometric actions. So we will see commutators with functions and commutators with unitaries implemented by potentially non-isometries.
Okay, so in other words, you have two actions, one of functions
Yes.
and one with
Yes.
with those gamma. Okay.
Yes.
May I comment on that?
Yes.
Continuing your question, Adam, you are right. You have some justified doubts at this point, because if you think about commutation between delta and gamma, it can be written as commutation of an automorphism and an operator. But if gamma is an automorphism, then the commutator of delta with this automorphism is not a natural operation.
Yes.
Okay? Because the commutator is for endomorphisms. If you are playing with automorphisms, then the condition of commuting of the operator and the automorphism would be like the conjugation of this operator by this automorphism.
Yeah, sure.
Equal to this operator. And the difference of these two is neither an automorphism.
I know. Here I'm not trying to be specific. I'm just trying to give.
But when it's zero, it's everything.
I'm trying to give the idea here.
Let me ask another stupid question. So every compact Riemannian manifold is measure the metric space, right?
Yes.
So is it automatically AHLFORS or
it depends which.
So you might have Riemannian metric on a compact manifold so weird that it will be.
No, for any Riemannian metric.
It will be AHLFORS.
It was the first example.
Yeah.
AHLFORS, regular space.
I just missed it.
But connected, yes? Connected.
Yeah. Or you can have like finding many components and yes. So the question is the following: can we extend Laplace-Beltrami operators on general AHLFORS spaces? And the second is, can we achieve so that this generalization of Laplace-Beltrami gives bounded commutators with non-isometries? The answer to the first is no. Because Laplace-Beltrami is a local operator. Okay, so it's specified. It's a local operator. So, and AHLFORS spaces also contain totally disconnected spaces, like undersets with ultrametrics.
And sorry, may I have a comment on my question to you?
Yes.
One colleague of mine, Piotr Hajłasz, was developing the theory of Sobolev spaces on metric spaces.
We'll come to that.
You will come to that.
Yes.
Yeah.
But it depends what Sobolev space you try to create, and I will come to that.
Okay.
So, The answer is no, because on totally disconnected spaces, you cannot have local diffusion. I mean, you get trapped, you cannot diffuse. You can only diffuse non-locally with jumps. Okay, so that's the first element to keep in mind. The second is, well, assume that we have a nice operator that is Laplace-Beltrami-like, okay, on your space. Can you achieve that the commutator with non-isometry is bounded? There is a technique developed by Bram, Magnus, and Adam Rennie, log dampening. So they take functional calculus basically, and they make the eigenvalues to grow slowly. Okay, and then you can achieve these bounded commutators. But the problem I told you is you don't have something to take the log of it. Okay, so somehow you need to come up with a non-local operator with slow-growing eigenvalues. Sobolev spaces. So how do we do it? Well, we focus on this. You need first a nice densely defined and closed symmetric bilinear form on your Hilbert space. The Hilbert space is L2 of X with base AHLFORS measure mu. And this is a bilinear form. It's densely defined. It's defined here. And I can tell you why it is densely defined in a bit. Now you can see that there is some singularity here. Okay, so whenever X and Y get close, it blows up. But the fact that your measure is AHLFORS regular really controls the blow up, the rate of that. Okay, and here is it. If you take a Y which is close to X but R away, then this will be like of order log of R to the -1. Okay, take everything less than 1, so it's positive. Okay. So
sorry, so it's still singular.
Yes, it's still singular.
But it's controlled.
Control. Yes,
asymptotics.
Exactly. Exactly. And now this is an unusual singularity, as you will see, but it's the one that one needs. It seems like the optimal that one needs to obtain bounded commutators with non-isometries. Now, to some of you, this might look like, hey, that's a fractional Sobolev space. And that is true. Well, the one I'm presenting is not fractional. But maybe you have seen this formula with some plus alpha, where alpha is between 0 and 1. Okay, and these are really reminiscence of fractional powers of the Laplace-Beltrami operator. But all the tools that have been created to study fractional Laplacians, where maybe I should have it here, or the way it's written here. Fractional Laplacians, they just don't work when you put alpha equals 0. Okay, so it's a very singular situation. And you see the logarithmic singularity. In the previous slide, I told you we want to create an operator with slow growing eigenvalues. And so I'm going there. But we had to create new techniques to study this very singular operator.
Sorry, yes. May I ask you a question? I'm trying to reconcile this content of this remark and this definition of this bilinear form. What happens if you abstract from the Cartesian square of X and R neighborhood of the diagonal?
Yes.
Do you obtain some consequence of but what is happening when asymptotically, if you are using this content notification.
Meaning this double integral.
Yes, yes.
If I subtract.
What's the consequence of this asymptotics for
it's going to be the same.
of this linear form? Because it's an integration with respect to x and y.
I guess it's going to be similar.
It would be similar.
Yes, because that's a uniform.
Because point-wise, you are fixing x, a point. Now I'm asking about integration of the diagonal.
It should be similar.
Should be similar.
Sorry, I believe that you are muted.
Okay.
Should never happen.
Thanks.
Yeah.
So how do you obtain an operator? Well, there is representation for this bilinear form, and well, it's densely defined, and I will tell you why this is densely defined. Probably, yeah, because I forgot. Well, if you take here, this formula, if you take a Lipschitz function, then and you put absolute values outside it, you use the Lipschitzness, you take the Lipschitz constant outside, and then here, and then you integrate 1 over the distance of x and y to the delta minus 2. And then you use the AHLFORS regularity and you get something bounded, something finite, okay? And now since you have all Lipschitz functions in there, it's densely defined. In fact, the domain is quite large, contains all other continuous functions. In fact, it contains more discontinuous functions, but if you know what it is, nice. If you don't, you can ask me, but it's not important, but it's like a very big domain, okay? And then we obtain a positive self-adjoint operator on L2, for which the domain of its square root is equal to the domain of the bilinear form, and in fact the bilinear form is given in terms of the square root of delta. Okay, and we call this the logarithmic Dirichlet-Laplacian, or briefly log-LAPLACIan. Now, the first thing that one can do is the following. One can see that the kernel of the operator here is really the constant functions, and the image of delta is really the functions of zero mean. Okay. And in fact, for these nice functions, in your mind, you can just keep Lipschitz functions. Point-wisely, delta has this integral representation. Okay, so it's a very intrinsic operator because all we have, the data that we have started and we haven't implemented anything more, is a metric measure space, x, d, mu. And here we obtain an operator x, d, and mu. The delta comes from the metric structure. Okay, so this is the operator, log-LAPLACIAN. Now I'm going to present you like many examples. Okay.
So could you comment on the definition of this Laplacian?
Yes.
From the point of view of integrations, it's over spheres around X, because of course we can define of course as harmonic functions as those whose average.
Yes.
Yeah. Can you interpret this definition of this delta in terms of such averaging?
Yeah. You can do that. You can do that.
Okay.
You can do that. Yep. Yeah, well, there are many things one can do. But important thing is that in this framework, if you want to do these averaging techniques and do stuff like that, and do some analysis, often you will have to change the metric and go to some equivalent metric. And this is fine for the level of Sobolev spaces. So changing metrics to equivalent ones, you can still work with essentially with the same Sobolev space, but changing metrics for the operator, it's a very hard move. Okay, so you really change the operator and its properties.
I have another.
But about the harmonic functions, next slide.
Okay, sorry. But for this slide, why logarithmic? What is
Because
logarithmic?
the singularity is logarithmic, and you will see in a bit how the eigenvalues be. So, Riemann manifolds. Well, here's the operator. Now, using heat trace asymptotics on the manifold, it's possible to show the following, that the log-LAPLACIAN is a bounded perturbation of the logarithm of the Laplace-Beltrami times this constant. Okay, it's a topological constant. So this is the volume of the sphere at dimension, that of the manifold minus 1. Okay, you have the 1/2. Now, from this, you can get that delta is essentially self-adjoint in Lipschitz functions, because you compare it with the log of the Laplace-Beltrami and plus bound commutator perturbation plus some bounded operator, and you get the essential self-adjointness from there. Moreover, you can see that delta has compact resolvent, okay, because the Laplace-Beltrami has. And moreover, using the first slide basically that I showed you, plus this constant, which plays a role, you can see that the heat operator, e to the minus t delta, for being compact, it's trace class for t greater than the dimension of the manifold over the measure of over the volume. So it's this number that appears, and we don't really understand yet. It will appear similar numbers in the next slide, but we don't really understand what it is yet, what it means, but it has some information of, like, I would use the same word, like volume, something like how large something is. And because of the fact that you don't have trace class for small t, but I mean, yes, it means that the heat kernel does not behave nicely when t is small, okay? And now you might wonder, why should we care about something that doesn't have a heat kernel all the way? Well, you cannot have everything. As I told you, we want to implement this operator to static dynamical systems, okay? And this seems to be an obstruction.
I cannot resist myself from asking a stupid question.
Yes.
Naively, if you have a logarithm of 1 plus something,
yes,
okay, you are tempted to write the expansion of the logarithm around 1. Okay, and then you obtain what? The Laplace-Beltrami plus higher powers of Laplace-Beltrami. But if Laplace-Beltrami is unbounded, then higher terms cannot be treated as small. So I have a conundrum. How this could be an analog of a Laplace?
It's the logarithm of that. And
yes, logarithm of 1 plus Laplacian.
Yeah, but you can take log of Laplacian, and it will be a bounded perturbation of the other one that you talk about. I'm putting 1 because...
No. Sorry. So this delta 0 is a bounded perturbation of that one.
Yes.
But I'm thinking about comparing this to the original Laplace-Beltrami.
No, it's not on the no, it's the logarithm of that.
It's logarithm 1 plus this. Yeah.
Or, but you have a bounded perturbation, so you can have like the log of the Laplace-Beltrami, but you kill the kernel, and so it's not the Laplace-Beltrami on the nose. I said we want to build spectral triples, and you cannot do it with something which is like actually Laplace, but something that comes from something that...
Similar doubts to Thomas. Why delta compact resolvent? For me, it is not clear. You have something which is approximately like log identity plus Laplace-Beltrami. Okay, Laplace-Beltrami has compact resolvent, but you're taking a log. So for me, it is not clear.
Why? It's like we are in a finite measure space, and so you really deal with eigenvalues here. So you have find.
So being compact is like tending to zero. So still logarithm is something which eventually grows to infinity. Okay, so this would be fine. Should be fine. It grows
But what
very.
is the negative power of 1 plus Laplace-Beltrami? This is typically, classically.
This is what means
compact
resolvent.
Yes. Yeah. Not 1 plus Laplace-Beltrami itself.
Yeah.
Negative power. Yes. So you are in some place you are inverting this function. So the growth of eigenvalues would be something like 1 over this this logarithm. Yes, something like that. So it grows eventually. It eventually tends to 0, but very slowly. Yes.
Yes.
So
Okay.
I suppose this is the idea.
Yes.
To make the growth of eigenvalues.
Exactly. Very slowly. But I need to move on because I have many examples to show you. So let's go to the other extreme.
Can I have one question?
Yes, of course.
So coming back to this operator, I mean, okay, if this is exponential.
Sorry? Can you show yourself?
I can show myself, yes. Okay.
Speaking.
Yeah.
Okay.
So e to the minus t delta, well, if it's not trace class for some small t, what could be said about the negative powers of delta? No negative powers of delta are, so delta to the minus n wouldn't be a trace class for any n?
No. Okay, no. So at the end, if the question that you have in mind is if we get finitely summable spectral triples, the answer is no.
No. Okay, yeah. So this is
something that we don't want finitely summable.
Okay.
Because we want to put them on cross products on dynamical systems.
Okay. Okay. Good. Thank you.
Might be
like 1 over log n. Yes. So this sequence has the property that the associated series is always divergent. Yes. If you take 1 over log, whatever power you take of it, it will be still divergent.
Yeah.
It is an example which of a sequence which is in C0 tends to 0, but is does not lie in any LP. Yes.
Yeah. Yes. And also, it's important that the thresholds I'm going to show, if I have the time, is that they are not 0. Okay. The other extreme, counter sets. You can do it more generally, but let's take 0, 1 sequences. So these are infinite sequences, and you consider their space. You put an ultrametric. You basically measure, count for how long these sequences are the same, and then the first moment they are different. It's your exponent here, and you take 2 to the minus that exponent. And you can put a nice measure, so a ball of radius 2 to the minus n as 2 to the minus n. So I'm just like super simple, okay? Now, you can describe the spectrum and the eigenfunctions, so you can diagonalize your operator, the log-LAPLACIAN, on the nodes, okay? The eigenspaces here are really given in terms of Haar wavelets, and you don't have a translation in that setting, but you have the notion of dilation because you really deal with here in the dyadic tree, so you can just keep going down the tree, and you can build these wavelets. these are functions that integrate to zero. And as I told you, if you remember at first, the image of delta from general theory, you can see it's functions that integrate to zero. So you obtain essential self-adjointness or Lipschitz functions, the wavelets or Lipschitz functions. They are finite combinations of characteristic functions. And you have compact resolvents. Again, you have a similar behavior for the heat operators. And what is interesting is that if you do it in more generality, here you're gonna get the entropy, the topological entropy of your shift. Okay, so that's another threshold of largeness, volume, or something.
Is the general results relating this T and entropy of the map?
Is it a general? Yeah, you can have it more general.
Yeah. It's an example of.
Yeah, here I just wanted to give you the extreme cases and want to be very, very, very simple. Okay. So you have this. Now
I have a small problem with your third line. Now, second from the bottom.
Yeah, sure. Yeah.
I mean, you say compact and trace class. So can it be trace class without being compact?
No.
Trace class is enough.
Yeah, I'm just.
But it is compact.
And trace class. If it's trace class, it's compact.
Yes.
In fact, trace class.
But when it is trace class, always?
No. It's always compact.
For T sharp.
So this is always compact.
Okay.
Yeah.
Trace class whenever this.
Yes.
Always compact and trace class only.
Yeah, but I think always would be helpful, yes.
Yes.
Only trace.
Yes.
Because, the question how we put parentheses in English, right?
Yes, yeah.
Okay.
Good point. I will change this. So, okay, let's go to something in between. The unit interval. You might think, okay, what should we care about the unit interval? Well, that has a boundary. Okay. And Laplacian on it doesn't have, it's not self-adjoint, you have boundary conditions. But here you have a problem. Well, how can we diagonalize the Laplacian on the unit interval? Well, we use this simple formula, okay, that everyone knows. And then you go to the integral and you compute it. In fact, you can find a recurrent formula for it. And here you get the eigenvalue 1, and this is the eigenfunction 3/2, 11/6, 25/12. What are these numbers? Yeah.
Rational.
Yes, that's a good start. Well, yes. They are the harmonic numbers, one by one. You get this number 2, but it's not important. It's how you define the metric. And so you get the one by one, the partial sums of the harmonic series. And they are simple, and its eigenfunction is a Legendre polynomial.
So these 2 corresponds to 1/2 of the.
Yeah. That's why I put it there, because I wanted you to see the harmonic numbers.
I also cannot resist to remark that 137 is very important in physics. One over this is fine structure constants.
But I think that's not connected.
I also think that this is absolutely not connected, yes.
But it's kind of interesting that you start with an integral formula that doesn't have the harmonic numbers in it, and you just pop out. Yeah, they pop out. And yeah, so that's a very interesting example, I think. And compact groups, not necessarily smooth structure. Okay. How much time do I have?
1 hour, 2 minutes.
1 hour.
And 2 minutes. Sorry, 47 minutes.
Okay. Thanks. Yeah, so compact groups. Well, if you have a compact group, a nice invariant metric and the hard measure, okay, like what is a compact group which is not smooth? Well, dyadic solenoid, for instance. So you can go to any topological dimension, you have all sorts of nice stuff. Then you can show that delta commutes with the convolution operation on the group. And as a result,
Wait, you assume that it's a Lie group, right?
no, just compact group.
You have this Laplace Beltrami.
It's a metric measure space.
Okay, it's a metric measure space.
So this is this log.
Yes.
Yeah.
Yeah, everything is log-LAPLACIAN. And it behaves like the actual Laplacian, so it comes with convolution. And in fact, because of that, using Schur's lemma, you can show that then delta acts by scalars on the Peter-Weyl decomposition of the group. And then you can also show that delta is essentially self-adjoint by Lipschitz function. Okay. In particular, now, if you have an abelian group, then in the Peter-Weyl decomposition, its reducible representation is going to be one-dimensional. So this means that the eigenfunctions of delta, in the case you are abelian, are simply the characters of the group, one by one. Okay? And then, if you want to compute the eigenvalues of delta, then you simply evaluate delta on a character at the unit of the group. Okay? So, yeah. Okay, and here are some general facts about the log-LAPLACIAN. Okay. Indeed, delta always has compact resolvent, and its eigenvalues grow logarithmically fast, as we wanted them to grow. And you indeed get a T0 for which this is trace class, the heat operators. After some time, they become trace class. And now the domain has a nice structure. It's a Banach module over continuous functions. And moreover, the commutators with multiplication operators given by continuous functions, they extend to bounded operators, but nice bounded integral operators.
Wait, so Banach module is like Hilbert module, but instead of a product given more.
Yes. And here's an interesting property, this one, that the Lipschitz functions are smooth in terms of delta. Okay, so they are in the domain of all the powers of them. And here, I want to say, to make the following remark. If we are in a like manifold situation, then we know that Lipschitz functions, they're almost everywhere C1. Okay? But here, we have that here smooth. Okay? And the C1 then becomes the Dimi continuous functions. This means that delta, it's really an operator of order epsilon or any epsilon positive. It's like it's bounded, but it's not, it's unbounded. Okay, but it's like infinitesimally small order. And you can also see that this very small order from what happens here, you take a polynomial of degree n, you get a polynomial, it gets mapped to a polynomial of degree n again, okay? Right. So there are some general facts. Now, well, this is the notion of speculative I will use. a Hilbert space and a scissor algebra of bounded operators, self-adjoint operator D, compact resolvent, and a Dess subalgebra of your scissor algebra that preserves the domain and commutator extends to something bound. And I guess I can skip this seminar. Good. So a corollary from the general facts that I showed you is the following, that for any AHLFORS space, the log-LAPLACIAN gives you a spectral triple where the smooth algebra is Dini continuous functions. Of course, this spectral triple does not have has trivial k-homology. The operator is positive, but we will get back to that. Dynamics. Okay, so now you will understand why we wanted such an operator with slow-growing eigenvalues that also makes sense on fractal situations. Limit sets of Lagrangian groups. So what's that? Well, you take the...
May I ask a question? So
yes.
Squared.
So could you go back to the previous slides?
Yes. Here?
So here, so now if we put it in the context of spectral triple, then this delta is playing the role of Dirac operator, not the...
Yes.
Not the
No, yeah, I mentioned, so you're right, notationally. In the first slide about the Laplace Beltrami, I used delta, but after that, the delta was the log-LAPLACIAN.
So okay, so is Laplace, is the delta positive? Usually not, right? So it's
Sorry?
so I mean, as Dirac operators, the eigenvalues could be negative, right? Usually, so
yes.
So is that this case? So the eigenvalue of this delta could be like have both positive and the negative parts. Both goes to infinity, for example, like in usual. That's the
No.
is usually positive or some. No.
It's always positive. This one.
So this delta is always positive.
This operator is always positive. Yes.
Then why not take the square root of this as the Dirac?
I will come back to that.
Okay.
So Lagrangian groups. Okay. So you take the hyperbolic space here, and then you look at the group of isometries of the hyperbolic space.
Isn't square missing here in the Poincare metric?
I don't think so.
Where do you want the square? What is dx?
I don't think so.
Poincare metric is a quadratic form on the tangent band, okay? So typically it's written d rho squared is equal to something. Dx squared divided by something depending on.
These are equivalent.
But what is dx now? So probably it's Euclidean length. Yeah.
So you take the isometry group of the hyperbolic space, and then you have that, okay, although this acts by isometries on the hyperbolic space, the boundary, which is a sphere, it no longer acts by isometries, okay? But it acts non-isometrically, but by nice diffeomorphisms. Conformal, exactly.
So not so distant from isometry.
Yes, but still, even for conformal, you cannot get bound to phasors. Right, so what's the fractal space here? It's the limit set of that group. And how do you build it? You take a discrete subgroup of the isometry group, and then you take any point in the hyperbolic space, x, like in the interior, and you let it flow. Okay? Now, no matter from where you started, which point you picked, it will accumulate in the boundary. And that's the limit set. Now, we study some particular groups that give a limit set for which the Patterson-Sullivan measure is AHLFORS regular. Okay. And here's a picture that I got from Wikipedia. And we are trying to create differentiation on such spaces, implementing dynamics also on top of that. And
so you mean to group to be of second kind?
I'm sorry?
What does it mean for this group gamma to be of second kind?
It's not all the sphere.
Meaning?
The limit set. So it's like some fractal in the sphere.
Okay. Thank you.
First kind means
It's the sphere.
is a sphere, full sphere.
Yes. But you also get the results for the first kind. It's just that they're more interesting. Otherwise, I would have to put many pictures here. Anyway, so indeed, with the log-LAPLACIAN here, if you take any element of your group and you consider the unitary operator on L2 of the limit set, the Patterson-Sullivan measure, then the commutators extend to bound it once, okay? And this is what we want to get. Now, eventually, also from the fact that delta gives a spectral triple over the continuous functions on the limit set, because that was all the discussion before going to dynamics. And from this proposition, immediately we see that we obtain a spectral triple for these cross points. And that's a purely infinite sister algebra. And I can go back to a question, I don't know who asked it, but it was about finite summability.
Wait, Adam? No, Andre.
Okay. If we started with something like the fractional Laplacians, Laplace alpha, they give finitely summable spectral triples, we would get something finitely summable here, if it was possible. But then this is purely infinite, and we cannot have finitely summable spectral triples. There's a tracial obstruction. I can't. But also, in the proof that we have with Bram, you can see immediately that if you have the fractional Laplacian, because that's an integral operator that I showed you before, f of x minus fy over the distance to the delta, and you integrate. If you had the exponents like plus alpha, like the Hausdorff dimension plus some small alpha, immediately you see that the commutators, they just blow up. So also you see it without using the heavy hammer of this tracial obstruction that you get unbound to commutators. Now, here, still, the K homology is 0 because that's positive, but there's a way by adding potentials, unbound potentials, here to obtain non-trivial K homology classes, and in fact you can obtain all the K homology of that. And now it becomes clear also from work of Magnus Goffing and Alexander Lachev, and who else worked on that? Maybe Adam Rennie, I think so. You obtain the following, that the threshold for when the heat operators are trace class is related to the inverse temperature of MS states or the Heisenberg flow.
So this is a conjecture proven?
No, they have a general machinery. They say whenever you have an operator with heat operators being trace class above a certain threshold, then you obtain KMS states.
So the second point is a fact.
The second point is a fact. But now one can go further and actually study
by this rule. I was confused by this rule.
Yeah. But
It's a theory.
Well,
but be related.
Exactly. So
this machinery.
It is related, but just saying it is related or writing down theorem, if you don't really study it and see what you get, so we haven't done it yet. So it is related and should be related in a nice way. It's open for investigation.
Yeah.
And as I said, the fractional Laplacian does not fit in this picture, but next week, hopefully, we're going to have a paper with Brown showing that fractional Laplacians, well, they don't behave nicely with dynamics, non-isometric dynamics, but they behave nicely with quantum metric spaces. And these don't give quantum metric spaces, the log-Laplacian. So if you want dynamics, actual dynamics, you need slow Brownian eigenvalues, and you get infinite distance, infinite diameter of the state space with a condistance. But if you want something more local, like it's still non-local, the fractional Laplacians, but it's more local, if one can say that, than the log-Laplacians, then you can see more about the metric structure. The log Laplacians see the conformal structure, the fractionals see the metric structure. Is what we're proving.
Okay, can we say that this proposition is equivalent to saying that action of this group changes this potential part of this log Laplacian? Because you said that this log Laplacian is something like bounded perturbation of something constant times log.
No, in the manifold case.
In the manifold case.
In the manifold.
Okay, so because you have this as an analog, so the action of this group creates some potential.
Yes.
Some bounded parts, which could be interpreted as a potential added to a Laplacian.
Yes. Okay. Yes, exactly. This is how you can do something like that. Yes, exactly. But the bounded perturbation is in the manifold case where you have heat traces in topics. And then you do computations and you get these numbers. Okay, so how much time do I have?
You have about half an hour.
Oh, good. And now I will show you work with Magnus Goffing and Brom-Esland, a recent one. That we use this machinery of the log-Laplacian. In fact, after understanding the log-Laplacian, we were able to go there. The log-Laplacian for metric measure spaces, we were able to go there. That you get non-trivial k-homology classes, you get all k-homology classes. In fact, you can generate them from the log-Laplacian class potential.
But before you do it, could you remind me, please, what is a Kleinian group?
This. A discrete subgroup, the isometric group of the hyperbolic space.
Limit set.
No. You take a discrete subgroup.
A discrete group subgroup, okay? So any discrete subgroup of SO plus N1 is a Kleinian group.
Yeah, you can define it like that.
Okay.
I mean, it depends what definitions you find, but yeah. But here, okay, so I will show you now how to use this log-Laplacian in a very interesting example. Kunst-Krieger algebras. Okay, Kunst-Krieger algebras, well, I would say we know quite a lot about their topological aspects. But studying their differential, trying to create a differential framework, then using like semi-classical methods, well, this is what we try to do, and this is what I'm going to present to you now. Before I move on, though, is there any question? Okay, so we start with an n by n matrix with 0 and 1 entries. And this should be viewed as the adjacency matrix of a finite directed graph.
And what does it mean, primitive?
Primitive means that the graph is strongly connected. You can go more general than strongly connected, but...
And strongly connected means whenever two vertices are connected by directed path?
By directed path of a uniform length, in the sense that there is a uniform number, m, let's say, so that any two vertices are connected by a path of
at most length.
You can find the path of length m.
Yeah.
And then for you can find paths of length m plus 1 plus 2 plus and so on between the two vertices, therefore.
Then we see this property from looking at the matrix.
Yes, so you have a power, it means that there is some n, so that the entries are only positive, because the entries really tell you how many vertices there are between, edges there are between vertices.
Yes.
This is what it says. So if you take a squared,
length 2. Exactly.
How many do you have of length 2?
Right, so you take a to the power n, and then what is the property?
That there is some n, so that a to the n has only positive entries. And now if you take higher powers than that n...
How can it have negative entries? I don't understand.
0.
Non-zero, okay, yes. All right, of course.
But you can go more generally, but already it's quite involved for the primitive situation. And on that, you have the left shift, you just shift right, but you kill the first entry. Okay, so that's not a homeomorphism, it's a local homeomorphism. And you have a nice measure, what's the Chandler measure again? All right, now the Kuhn-Kruger algebra, it's the structural algebra generated by n partial isometries subject to these relations here. Okay, so you want the range projections to decompose the unit, and also you want the source projection. Oh, I thought I was using that. And you want the source projection at the vertex I to be written in terms of the range projections that I can go in the graph. And also you want the projections to be mutually orthogonal. Now, these are really nice sister algebras, and they are close to being manifolds, simply because you have a Poincare duality or KK duality. It means that the K theory of OA is isomorphic to the K homology of OA transpose with a parity shift. And it's really a generalization of Poincare duality for manifolds. And that was proved by Kanker and Putnam in the 90s. Now, as previously, there has been NCG approaches for OA, but in a more algebraic setting, in the sense that
sorry, you're using the opposite convention, right? So for you, the Teplitz sister algebra would be a graph sister algebra of an incoming. Sorry.
Yes.
This is why I was so confused by what you.
Yes. Yeah, it depends on what you choose, but once you get used to something, it's hard to read your mind around. So more algebraic approaches in the sense that you find a nice Hilbert space in which you represent your algebra, you find a nice eigenbasis of that Hilbert space, and you pick eigenvalues to create a nice spectral triple. But here we will try to go deeper using actual analysis. That's when I showed you, like what I showed you before, using integral operators on Kunstkrieger algebra.
In fact, there's a representation which comes natural with such sister algebras. Shows you that if you go to the Levitt path algebra, which is before taking the completion, but in fact this is always a sub-algebra. So when you do the universal sister algebra, you don't have to do the equality, just take the completion.
Yeah.
So that's this is a very nice star representation on the Hilbert space.
But here I will be less algebraic because we want to use these integral operators. So far we don't have points. We have a space, but not of points. And to create a space of points, we focus on the groupoid picture of the Kunstkrieger algebra. So what's that? So you have a shift space, and think of n being equal to 0, this integer being equal to 0 for a moment. And then this is really saying that there is some k, so that if you shift x k times, like
Sorry, but what is sigma a?
The shift, the left shift on the shift space. This is the shift space, so space of infinite words.
Okay.
So for n equals 0, this says that x and y, they are tail equivalent. Okay? And now allowing n to be whatever, you introduce some lag. So this is how I view this, like
infinite words in edges.
Yes, in vertices here, because it's like 0 and 1. So it's like, let's make it simple. Yeah, the symbols are the vertices of the graph.
So these are not paths.
No. But you can go also to paths, and I will explain.
Tails.
Yes. I will explain a bit. I'm just trying to give an example here. Now, this is a groupoid with this partial multiplication, and you can equip it with bases of bisections. And these are the cylinder sets of alpha and beta, where alpha and beta are some finite words in your language. And now OA is canonically isomorphic to the groupoid sister algebra of the diagonal groupoid. And the map is given by taking the generator Si to the convolution operator of the characteristic function of this set here. I is like a symbol, so it's a word of length 1. And this is basically the picture of Si. How do I want to say? That Xi is the characteristic function of x, 1, sigma x, so that x is in Ci. So x starts with I. Okay, all these words that start with I.
And what is this p chi I?
It's the convolution.
Convolution with this guy.
And then
in this groupoid.
yeah, and then you see that you check that they satisfy the Kunstkrieger relations. Okay? So it's a canonical isomorphism to the groupoid sister algebra. Okay.
Sorry, you said that it's a canonical isomorphic.
Yes.
But in the definition of this characteristic function, you are using a choice of x from the Ci.
Yes.
So it is so it must depend only on I, and it is independent of x.
Yeah, x is like all the x that are in I.
So okay, so it's your notation for okay.
Yeah.
I understand this.
Yes.
column.
So that's the more, let's say,
A set of such examples.
classical picture of Kuhn-Krieger algebra. Okay. And now the next slides.
Could you tell me again what is the CI? Just alpha beta, what is CI?
It's the cylinder set in your shift space. So all words that start with I. Just that.
Okay.
Okay. So next slide. I'm gonna skip the next slides. I won't dwell much on them. Well, coming back to the log-LAPLACIAN, this is a nice counter set, has a nice fractal dimension, and you have a log-LAPLACIAN, which is densely defined and positive, essentially self-adjoint on the locally constant functions, compact resolvent, and gives a spectrum chip over a commutative circular algebra on the shift space. Okay. And
what is TMC?
Topological markov chain. Sounds more serious. So,
sorry. So
yes.
So these are locally constant functions.
You can go to Lipschitz functions or yeah. But I mean that's small. You can go to Lipschitz folder DIM continuous. It still works, but if you are in a counter set, you just work with locally constants. It's much easier. All right. So the idea is to extend, because the shift space is inside the groupoid. It's the unit space of the groupoid. And on the unit space, we have the log-LAPLACIAN. We want to extend it the whole groupoid. And indeed, it's possible. We put a metric measure structure on the groupoid.
On arrows. On all arrows.
Yeah, on the arrows, in the space of arrows. And then, indeed, the log-LAPLACIAN from the unit space extends to the whole groupoid with the same formula here. Okay, so we do have the log-LAPLACIAN on a groupoid. And there's some work here that I'm hiding under the carpet, of course. But yeah, I can explain more, or I can just move on because it's more important to show you what you get out of that.
So your integration now is against the
system. Yeah.
So our measure is our system.
Yeah.
But wait a minute. But
so this measure, this
is a collection of measures.
This
measure on the whole space of arrows.
The L2 space of the groupoid. Okay. That measure, it's the GNS space of the KMS state for the gauge action.
Okay.
On the Kuhn-Krieger algebra. And there are many things happening here. I just want you to keep in mind that it's possible to extend the differential structure that we have built on AHLFORS regular spaces, in particular for topological Markov chains, to dynamics, okay, to get it on the groupoid. And also I won't dwell here.
Sorry, you had something like C infinity. So what do you mean?
C infinity, I mean locally constant functions.
Okay.
Here, yes. Compactly supported. All right. So indeed, now we can do a lot with this log-LAPLACIAN and the groupoid. The first slide, just want you to, I overloaded it to show you that we can do a lot in terms of spectral theory. Well, you can you can diagonalize the log-LAPLACIAN on the nose. And in fact, again, you get far wavelets, but now on the groupoid level. And I won't try to explain everything here, but I want you I want to stress out the following, that this is a function in L2 of the groupoid. In fact, it's a locally constant function, compact support. And this is an eigenfunction of the log-LAPLACIAN. And in fact, all of them are of that form, and they depend on 3 variables here. Okay, they move and you get all the eigenfunctions. And its generator, SI, acts on L2 of GA, in this GNS space, and we know exactly how it acts on the wavelets, on the eigenfunctions. Okay, and all these are the possible ways that it acts. What I want you to keep in mind is that more often it happens the following, so this is a parameter that depends on a finite word alpha and a finite word beta, and SI acts on this eigenfunction by really shifting the parameter by I. Okay, so it's multiplication of the level of the parameters. So you take these wavelets, SI takes these wavelets to that wavelet. But now, if alpha is the empty word, then it gets more complicated, and it's always the empty word that creates troubles.
So this circle is the empty word.
Yes, yeah, it's always the empty word.
But and when you say multiplication by I, what exactly do you mean?
The concatenation.
Concatenation, exactly.
Oh, sorry. Yeah. So these are the eigenfunctions. Now the eigenvalues, again, I won't dwell here, but I want to say the following, that since we haven't made any choice on this Laplacian, okay, it's an intrinsic operator. Okay, then it becomes, you need to try to diagonalize it, you need to put some effort, but after you put some effort, you get to see a lot of the structure that you started with. And so these are the eigenvalues of its wavelet, and I just want to say that they depend on finite words in your graph, or finite paths in your graph, mu. And then the eigenvalue at mu is given in terms of transition probabilities from mu at position to mu to the next position. So like you have mu is mu1, mu2, mu3, and so on. And the eigenvalue at mu, it's really given in terms of transition probabilities of going from mu1 to mu2, mu2 to mu3, because you might have more choices, okay? And the eigenvalues really tell you how much strongly connected the graph is.
So P now means what? Probability?
The transition probability of going from mu2 to mu3. Okay, so we know the eigenvalues, and in fact, you can do even more. That was, I think, the remarkable. I think we didn't expect that something like that would happen. We can write down a closed formula for the heat kernel, and indeed, on the diagonal. For small t, there is some t0 here, so that the heat kernel is singular, it blows up. And after that, it's nice, a nice continuous function. And it's given by this closed formula. I haven't written down these expressions, these functions of t, but they are in the paper specifically written. That's not the point. You see here that it's really given in terms of the distance of x and y to some power, where if t is small, this becomes 1 over something and blows up. And if t is large, it's nice. And what we didn't expect was that, except for finding a closed formula, was that the heat operators are Riesz potential operators. Riesz potential operators are operators of this form, like Fy over dx y, like Riesz potential operator S to the I tried to erase it with the hand. Minus S d mu y over x, okay? So it really, you really get something like operator that you find in classical analysis of Euclidean spaces.
Our functions h little and capital H unity determined?
Yes.
And the constant C?
Yes. It's written on the nose. Mm-hmm. It's just that they're not functions that one could come up with because for it to be a heat kernel, you need to satisfy many properties. And yeah. So that's about the spectral geometry. Now the K-homology. So let's focus here. Indeed, you can recover all the K-homology. And how do you do that? You have a Fock-like space made out of the kernels of log-LAPLACIANs, which you break the log-LAPLACIAN into smaller parts. And the kernels, if you remember at the start about metric measure spaces, the kernels are really the constant functions. Okay, so they are one-dimensional. And you have a Fock-like space inside L2 of GA. And then you consider the projection from L2 of GA onto the Fock space. And this projection here. And now minus the log-LAPLACIAN plus this 2 times the projection minus 1 times V, where V should say it here. V is a positive unbounded potential that comes out from this decomposition. It's really a level scaling operator that measures in which level of the decomposition you are. This is again a spectral triple over the locally constant functions of the groupoids, so over the Kuhn-Krieger algebra. And in fact, through Poincare duality, where the duality was K0 of OA transpose is isomorphic naturally using Kasparov products with K1 OA. And so you have the class of the unit. Oh, that's a bad unit. All right. So you have the class of the unit in here, and the image, it's really the class of the spectral triple. And in fact, you can do even more. By varying this Fock space using finite paths and creating for each finite path in your graph a Fock space and taking the projection on that and just having minus delta plus 2 times the projection on this Fock space that depends on a finite path, just start with any finite path, minus 1 times this scaling potential, then through Poincare duality, the image of the class of projection is the class of this spectral triple. So you get them all. You get them all through Hamiltonian type operators.
Sorry, I'm a bit confused about the notation. This OA means the graph sister algebra, the Kunst-Krüger algebra, the even matrix.
Yes.
And how come at the end of this transpose?
That's the duality. That's from the duality. Because when you try to prove Poincare duality, you need either to consider some opposite algebra or some transpose, like you need to reflect, to create enough space to prove the duality.
Yeah, because transpose is like taking the opposite algebra.
Yeah.
You're right.
And so we get them all using log-LAPLACIANs.
May I ask a question? In the classical Fock construction, it's a direct sum of some
all the words
operations on something.
Yeah, but all the words that you can create, the finite words.
Mm-hmm.
But here it's a bit different. You don't allow all the.
So they are tensor powers of a single one-dimensional vector space. So these eigen spaces.
So I need to explain you what
tensor powers of a single one.
Yeah, yes. I need to explain you what this means, which I skipped. So alpha and beta are arbitrary finite paths in your graph, for which the last letter of alpha can be concatenated with the last letter of beta.
Last or first?
Last. That's why we have put a dot. So it's like taking an opposite. Equivalently, alpha can be concatenated with the representation of beta. Exactly.
Morphisms in the category.
Yeah. Yeah. And so parametrizing the complex numbers over these creates something, because you have some. It's not that for a beta you have a unique alpha. You have like plenty alpha, and then basically you can have the Fock space, the classical Fock space, and then if you want to localize it at some beta, you will have to kill probably some words that at the end do not concatenate with this given beta.
So in a sense, it's a quotient of
yes, in a sense.
Okay, yes, good.
Yeah, exactly. Yeah. Okay, so spectral geometry we saw, the homology, and
we are speaking about Hamiltonians. So by Hamiltonians, you mean that you have Schrödinger-like operators.
Yes.
Laplacian plus some potential.
Yeah. Yes.
So speaking about Hamiltonians, you actually mean potential.
Yes.
Okay.
I'm not trying to be a formal by this terminology, but philosophically it's something like that. And at the end, that's the last slide, we can see symmetries, okay? As in the classical situation where you can read the symmetries of a Riemannian manifold from the Laplace Beltrami. And going back to Goswami and other people, they have studied isometric groups of manifolds and of spectral triples more generally, and quantum isometric groups. But it all depends on the spectral triple that you're going to work with. And for Kunst-Krüger algebras, that hadn't been done because...
I'm sorry, but it's really a shame. Dan Voiculescu was all the time at your talk, and then he vanished when his name appears. Such a shame. I mean, he was all the time listening to your talk, just vanished a minute ago, and now his name. Oh, he's present. He's present, he shifted from participant to slot. It has to be the preserved number of Voiculescu. Conservation of Voiculescu. Okay. Anyway.
So... what they want to say.
Sorry, I distracted.
Yeah, so so in the past Rossi and Conti, they had studied isometric groups for Kunz algebras.
Yes.
Using some spectral triples constructed for Kunz algebras.
Yeah.
And
we gave a talk at our segment.
okay. And they had shown that the isometric group is the unitary group on the number of symbols. I mean, the dimension, like the UN, where any number of symbols. But for going to Kunz-Krieger algebras, complicated. And it looks like you need to have a spectral triple that you understand well. And this is what we have here. But still, we really didn't expect to be able to compute the isometric group on the nodes. But before going there, let me give you some backgrounds. For this spectral triple, I'm just specifying it here. You can define it more generally, what an isometric group of a spectral triple is.
And sorry, what is this n in the power of a torus?
Is the number of symbols.
So it's the size of your matrix A.
Yes, it sees that. So what's the isometric group? It's really the group of automorphisms of your Kunz-Krieger algebra, for which there is a unitary implementing them. And that unitary commutes with the operator in the spectral triple. Okay. So now, I mean, everything's happening in the GNS space of the KMS state for the gauge action. And so that's the definition. And to try to compute the isometric group, you basically need two steps. The first one is to try and see where this isometric group lies. Okay. Well, you have read the theorem, I guess, that the isometric group is isomorphic to these semi-direct products. Alt A is the automorphisms of the finite graph, finite direct graph. Okay. And they act by conjugation on, by permutations on n copies of the torus, of the circle.
The gauge. Or the gauge.
Yes. And in fact, here you have the gauge action also, but that's larger.
And this gauge action, I suppose, is diagonal in Tn.
Yes. So, yeah, I mean, one way to view it is like
independent every vertex.
Yeah, here it's independent, but you can fix
one lambda for all.
Yes, and not consider that. Okay, so how do you show that the isometry is inside T to the n? Okay. Well, you need first to check that the isometry group, these automorphisms with these properties here, they embed into UN, the unitaries, which is not trivial to do. But after you do that, then you ask yourself, okay, I know that my automorphism in the isometry group looks like that. Yeah. Anyway, it looks like that. Okay. But which out of these really give an automorphism of a Kunz-Krieger algebra? And there is a way to specify that. So after doing these two things, like trying to understand that the isometry embeds into UN, and then which of those extends to an automorphism of a Kunz algebra, this polynomial automorphisms, then you end up to this inclusion here. Okay. But now to show that the semi-direct product is inside the isometry group, well, you have to see how this group here, why doesn't it write it? Yeah, have to see. It's not right. Maybe the,
I don't know, it should be right.
yeah, just
Right with the mouse and you cannot write.
yeah, maybe the battery, I don't know, but it's fine, I don't.
Maybe you can use your finger.
Ah, yes. Yeah, I forgot.
Well, your battery is also down.
But anyway, so we have the one inclusion, but to show that the semi-direct product is inside the isometric group.
Like this.
Exactly, thanks. Then you check how this acts on the level of the group points, basically. And then you see that it acts isometrically because we have a metric measure structure in the groupoid.
You mean groupoid or groupoid algebra? How this?
The groupoid algebra, yes. Yeah, the groupoid algebra. You need the groupoid picture.
Yes, yes, I agree.
And you see that it acts isometrically. And going back to the compact group situation here, sorry for skipping that fast, but it's almost there. Where's it? Here. We know that log-LAPLACIANs commute with isometries.
Yeah.
Okay.
Continuity.
And so you get the containments. But to do all this, you really need to have a fairly good understanding of the spectrum of the log-LAPLACIAN layers. Okay, it's a non-trivial task. And now a sanity check is the following. In a compact metric space, if you have an isometry, it has zero topological entropy. These isometries, do they have zero topological entropy? And the answer is yes. Okay, so that's a sanity check. Because we want to view the consecutive algebras not as non-commutative manifolds from Poincare duality, but non-commutative smooth manifolds. Okay, so we want what we have for Riemannian manifolds. Okay, and conclusion is we have a spectral triple integral with integral representation on the consecutive algebras. And it's trace class after some point, so related to K states. Closed formula for the heat kernel on the groupoid. Explicit description of the K1 homology, and an explicit description of the isometric group of OA. And we hope this will be a blueprint for general classes of groupoid algebras. In particular, this should be generalizable to graph algebras, so on, but you can go away from the zero-dimensional setting. As I showed you, we have it in limit sets of Kleinian groups and these transformation points, and you can have it more generally too. So that's all, and I thank you again.
Thank you so much. Let me ask you some immediate questions. So first, when you look at K1 of graph sister algebra, it's always totally free. It's always a free group. So I suppose K homology is just dual K theory, K1 to K1. So don't we always have an explicit description of K1?
Yeah. So the point is that it's not that we don't know what K1 is, of course we know. But it's a good indication what you can do for more general situations. And in fact, obtaining the K homology in terms of low spectral triples is a good indication that it's not void what you are trying to do. It has content, topological content, and content in the setting of spectral geometry.
Yeah.
Okay. So
they have nice representatives.
Yes. Exactly.
K homology classes, even though we have other presentations.
Of course.
Nice algebraic formulas and so on and so forth, and formal duality because we are torsion free.
Yes.
But still is something which is very particular to graphs. And you might want to beyond understanding the spectral triple.
Yes, exactly.
Okay.
So we want something that, ticks the boxes. And then we're like, okay, let's try to see what happens in more general situations.
And now, in terms of graphs, can you remind me what is Kunsttrigger? So Kunsttrigger is given by graph with which following properties. One of them is fully that is row finite, so no infinite emitters.
Did you hear everything was finite?
Yeah. So okay, yeah, also it's fine. Okay, so you have finitely many vertices, finitely many directed, yes. And what else? How about sinks and sources? Do you have some?
The way I presented it, no.
Because
But
you can have zero.
yes, exactly.
Okay.
But
So it's basically finite directed graph. That's all.
yes, yeah, but it should be generalizable. Even for primitive situations, like strongly connected graphs,
It's actually
highly non-trivial
to use this assumption because this is
this assumption, that's a good point. Where is it? Here. So you can compute the Hausdorff dimension from the Perron-Frobenius theorem. And then you know that the Hausdorff dimension of sigma A will go to the Hausdorff dimension of GA will be the Hausdorff dimension of sigma A because of the way the groupoid is constructed. It's local, like the range and source maps are local homeomorphisms. But then we have this decomposition, so the log-LAPLACIAN into smaller ones so that we can work and do some calculations. And because of the strongly connectedness, all the log-LAPLACIANs, the smaller ones, still are built from an integral operator with the same Hausdorff dimension. Okay, so does it make sense? It's self-similar in a nice way. But you can generalize this, of course.
So you used it on that slide, so to say.
Yeah.
To have this last point.
Yes. And then you can make you can get a Watervine law for the eigenvalues of that, some like logarithmic type while law, because of the primitiveness. Because it's closer to be like a connected manifold or something. So it's like you can make more specific statements. But then if you don't have a strongly connected graph, there are ways to break it to parts that they are strongly connected or ones that permute cyclically and under the dynamics. And yeah.
Okay, so now anybody else? Sorry, I started with questions, but I love graphs hysteresis and I resist having the immediate questions. Okay, now anybody else? Tomek, Adam.
I have a question. How do you use this Markov property?
The Markov property, yes. The Markov property, it means that here, let's say.
Yes.
Or no.
No.
One back here. The Markov property tells you the following, exactly the following, that if you have a finite word and you want to extend it, you just need to look at the last letter. So it's memoryless.
Yes.
Now you can have longer memories. For instance, let's say that you want to remember, the previous two, the previous three, and so on. This is extendable to that.
So it's not necessary here.
No.
For the sake of simplicity, we are assuming this Markov property.
Yes, also in the paper, because we just wanted to give a blueprint. Okay. But it's extendable to many situations. Yes. And we didn't do it because we didn't bother, but because it was already very involved here. We tried to do, harmonic analysis on this. So
this makes especially these eigenvalues.
Yes.
simply expressed in
Exactly. So one thing because we want to diagonalize the operator also here. I write.
Yeah, but we'll try. I don't know why it's supposed to change, but try with a mouse.
So you can go back to how you build hard wavelets. I could write on the board.
No. I don't know what happened. I don't know why. Okay, suddenly it's.
So just forget about what's written on the slides and try to let's focus on the shift space of 0 and 1 sequences that I had in the previous slide. So you can view it as a tree. That's the root. That's no. Well, I can build it above. Okay, so these are two. These are the kids. These are the kids of the kids. Okay, because you can build and so on and so forth. And it keeps going. And here at the boundary, that's a bit bad boundary, but it's
at infinity.
At infinity, it's the shift space.
Yes.
All right. And now how do you build the hard wavelets, which turn out, due to their properties, to be the eigenfunctions of the log-LAPLACIAN? You consider the characteristic functions on each cylinder set. These are the compositions of your space, finer and finer and finer decompositions down to infinity. And on each level, that's level 0, that's level 1, level 0 is constants. Level 1, level 2, and so on. You consider the span of the characteristic functions on each level. And now you take the projection from the L2 space of the boundary to the span of the characteristic functions at level n. Okay, so you have, for each level, you have a projection from the L2 on that. And one projection, Pn, let's call them, is smaller than Pn plus 1, because you can write characteristic function at level 1 as like the sum of the characteristic functions on its children. All right. And now you take Pn plus 1 minus Pn, still a projection, and you call it Qn. And now all these Qn, they spectrally decompose your sum article. Exactly. Now, the strong connectedness comes from the fact that you want to do Gram-Schmidt, basically, because you want to find eigenbases for the images of the Qn. And how do you do that? If you start from the root and you want to have a basis for Q0, this will be eigenfunctions constructed from like characteristic functions at level 1. But to do the Gram-Schmidt, you need to to remove one kid every time. And you do it for every vertex. Let's say that you have the full shift on 100 symbols. You take, for each vertex, you focus on the 99 kids. Any of 99, okay? So you remove any of the kids. And you do the Gram-Schmidt. But now, if you are not strongly connected, it can happen that a vertex has only one kid. And then if you have to remove it, what do? You can't. So you need to go deep down. Okay? You need to go down, down, down the graph until you find a vertex that has 2 kids at least, so that you could do the Gram-Schmidt. Now, the strong connectedness allows you to do that because you can go down in a uniformly manner, because you have this uniform number m that you can connect any 2 vertices by a path length m. Okay. Now, you can go away from the strongly connectedness and the connectedness situation and remove the isolated points that you get at the boundary and all this stuff. But you need to keep track of all these things. So this is what it's not It's not a problem. It's not that it's not going to work. It's that it's more complicated.
So it makes the
makes
construction of wavelets easier.
Yes, which is already not easy.
Okay.
Yes, for the group oil. Yeah, I hope that helps.
Yes. May I ask another question? In the case when you have this homology dual to concurrent duality.
Yes. Yeah.
In this, so the situation is similar to smooth manifolds.
Yes.
Can you take then the exponent of this logarithmic, subtract the identity? Okay. If you have
yes. So to get an actual
to get something like an actual Bernoulli Laplace.
Probably, but I don't know if you would get a bounded commutator. I don't know if you would get a single triple.
So this boundedness of the commutator is in fact boundedness of the commutator with this exponent of some.
I see. I see. Like because we started with, we cannot have an actual Laplace Beltrami in this generality because of like totally disconnected spaces, and then we have something that behaves like in the classical situation for manifolds. It's the log, or other. So why not take the e to the? Yeah, exactly.
So what was the classical meaning of boundedness of this operator with something like heat kernel with an automorphism? It must have some classical interpretation.
Sure. I don't know.
It's elusive to me.
Yeah, I don't know.
Okay.
I don't know. But we thought about that, like, hey, now we have the log, so why not take that? Exactly. That's probably something to be investigated. So.
Thank you. I'm done.
Anybody else from the room? Anybody from Zoom? Andre? Yeah, muted.
Yeah. Just one very short question. I mean, when you construct the things for instance, for the fractals, is there any relation to the construction of spectral triples by Pearson-Belissard, for instance?
No.
No, not at all.
No, not at all. I mean, these spectral triples are odd, first of all. And second, they are intrinsic. We don't make any choices, like zero choices. We start with a metric measure, metric and a measure on a space, and we get a spectral triple that depends on that metric and on that measure. We don't have any choice function, and I would say it's very intrinsic, and that's why you get to see all these properties and they spit out because it's intrinsic.
Yeah,
if it wasn't, you wouldn't be able to learn more. But
okay. Yeah, thank you.
Anybody else?
Thanks.
I have another question.
Go ahead.
From this, let's say, Hamiltonian or Schrödinger point of view, if you consider classical Schrödinger operator like Laplacian plus some potential, then analytic properties of this operator depend a lot on asymptotics of this potential.
Yes.
It's a big
So you, when I was talking about some analytic properties, you went out for seconds.
So boundedness is one thing, but what can you say about some asymptotic? A relation between asymptotic of this potential and some properties.
So let's have a zero potential.
Okay.
Starters. I said that this is a metric measure space as before, and in the intersection of all the domains, we have the Lipschitz function, which is weird because Lipschitz correspond to C1 functions in the classical situation, but here they're smooth. But I explained that because it's an epsilon order, so for the epsilon for any epsilon, this log-LAPLACIAN. All right. Now, these are delta smooth, but we don't know if they are analytic in the sense that you can have like Taylor expansions. So we don't know, even for the zero potential in general, that you get nice analytic functions. Well, when you diagonalize it on the nose, yes, you know analyticity and so on. So that was, and this also.
What about the eigenfunctions? Are they analytic? Like harmonic?
Yeah,
They are. Okay.
yeah, for that, yeah, I mean, they're the eigenfunctions. So, but in general, we don't know. And literally, we're trying hard to understand the analytic properties. But yeah, probably it's possible, but when you are focused on a specific way and you think about this too much, you don't lead to somewhere. Probably you might be able to describe a subalgebra of C of X, for instance, for which, or at least that is inside analytic functions. I don't know, in the generality. In the examples, you can describe analytic functions. Now, after you understand this, then you can add potentials and ask more general questions. Yes, but this generality, I don't know. My guess, my hope would be that the Lipschitz functions are analytic. They're smooth, yes, but analytic is something more. That is my hope. But
yeah,
I don't know.
But this is very far from results of the type, if your potential, this is bounded part, is this and that asymptotics.
Yeah.
Then
yes,
then eigenfunctions are of that.
Yes,
like that.
Yes. I mean, that was a difficult, challenging problem, I would say, to be able to study so specifically a generator of the Sobolev space in terms of noncommutative geometry. And definitely there are many open questions there, and try to do harder analysis on that.
Okay, I'm good.
Okay, the last call. Young, Elmar, whoever. No? Okay, in this case, let us thank our speaker again. Thank you. I stop recording.